a look at some more complex logic gate circuits. So in most of these examples you'll be dealing with 3 inputs, and you can see on the left I have 3 switches with 3 light bulbs. So the switches are my inputs and the light bulbs are my outputs, and they're labelled A, B, C. Now at the moment they're all switched to off. So one of the possible combinations we can have is 0, 0, 0. If we now consider the 7 other possible combinations, we could have A off, B off, but C on. So that would be 0, 0, 1. We could then turn off C, but turn on B, and that would give us 0, 1, 0. We could then turn on C, and we get 0, 1, 1. Okay, now we're going to need to think about A. So let's turn A on, but the others off. So 1, 0, 0. Maybe it's going to help if I draw in these lines as well. And now we can have A on and C on, so that would give us 1, 0, 1. 2 to go. We can turn C off but turn B on, and that would give us 1, 1, 0. And the final combination is when all of the switches are set high or turned on. So that's how we set up a truth table for a logic gate circuit with 3 inputs. Now the trick to that, to do it quickly, is by following this pattern. So we have our 3 inputs, A, B and C. And the quick way of setting this up is to follow a pattern, and it works a little bit like binary. I'll just put those numbers there and come back to them in a second. So we start off by having 4 zeros in the A column. 1, 2, 3, 4, and then 4 ones. 1, 2, 3, 4. In the B column, we follow the same pattern, but alternate after 2. So for example, 1, 2, 1, 2, 1, 2, 1, 2. And when we come to the C column, we're now alternating every other one. So it'd be 0, 1, 0, 1, 0, 1, 0, 1. So that's a quick way of setting up your 3 input truth table. If you only have 2 inputs, the same rule applies. We use a pattern of 2, so 0, 0, 1, 1, and then we alternate it to 1. And that was in a previous video. Okay, so let's take a look at this combinational circuit. So we have inputs A, B, and C, and over here we have P. Okay, now in order to quickly set up this truth table, I'm going to follow that pattern. So 1, 2, 3, 4, 1, 2, 3, 4. It could get quite confusing without these lines. And remember, it's now alternating every 2 rather than 4. And now it's every 1. So I've very quickly set up every possible combination. So let's have a look. In the first row, we have 0, 0, 0. So A is off, B is off, C is off. And guess what? P will be off also. Let's follow this truth table. Let's turn C to positive. Now when we turn C to positive, look at the impact that it has on P. It turns it to 1. In the next column, the next row, sorry, it's 0, 1, 0. So C is off, but B is on. P is still 0. And then we have 0, 1, 1. And you can see the effect on P is that it's a 1. Let's do this without the help of the software I've set up here. So let's follow 1, 0, 0. Now a 0 going into an OR could still possibly give us a 1. So let's consider the first bit here. 1 and 0 into an AND gate or that's going to give us a 0. So when we get to this over here, we have a 0 coming out here and a 0 going into an OR gate, which gives us a 0 at the P. Let's check that. Yeah. Okay, next one. Well, I don't even need to work out the A and B because I know I've got a 1 going into an OR gate, and that will always give me a 1. So if we just check that one, that works. Okay, and when we get to the penultimate row here, 1 and 1 will produce a 1 or 0. So this will be 1 because 1 and 1, a 1 into an OR will produce a 1. And at the bottom, all three of them on, well, should be obvious, that will give us a 1. So that's how to construct a truth table for a combinational logic gate circuit.